what is the K? And K is a concept, new concept. And from this is a radius of gyration. K is the radius of gyration. So whenever you solve a problem, you need to determine the beam problem of this compressive loading, and you need to consider whether you can use this Euler beam, treat it as Euler beam, or you need to use this parabolic formula. And how to do that? First step is to calculate the critical slenderness ratio, right? L over K parentheses subscript 1. To get that one first, and then compare the actual slenderness ratio of your beam. If your actual slenderness ratio is greater than this critical one, you can use Euler. You treat it as your Euler beam. Otherwise, you need to use this is a parabolic formula. So this is very important. So it will appear in our exam to be given during next week, Monday. So let's continue. So we have finished this one. I want you guys to take a look at this example again if you have not fully digested what I told you. Make sure you understand all these steps. Okay? So as I said, a similar problem, I will change some parameters, change some conditions. You guys should be able to solve the problem. Question? The gentleman? No. Okay. Questions? No question, right? No questions for other problem for this. For this example, and I will not go through this example. Okay, so you can just take a look on what I'm interested in. This is Euler beam. So the parabolic beam is you can just take a look. Whenever there is a chance, there is a need, and you can use these two equations to solve. So this example, I'm going to ignore also. And here is a stress or the short compressive beam. So short beam, the buckling is not an issue anymore. So here's a strut. If we have eccentricity, so that means the load is applied not at the center, along the center line. So we need to use this equation instead. Okay. So take care of the compressive load and also the resultant the moment and the result from this P. M equals P multiplied by the E. E is the distance between the P and the center line. So this is sigma C. No, this one. So this is not a function of length. You can see that not a function of length. This differs from secant equation in that it assumes small effect of bending deflection. So here, if bending deflection is limited to 1% of E, then from the previous equation, so there is a limiting slenderness ratio for strut is uses L over K. So this is subscript is 2. So this one is different. So for our previous example, I have LK, this is parenthesis 1, right? Now, some students, I think at that time, some students might be wondering why they say use 1, not 2. Here's the reason. This one is for the strut. So here is an example. You can just look and use this equation to calculate, and use this equation to calculate the critical the slenderness ratio. So this elastic stability, you can see if I have a beam here, if I apply a load here, so if it's a stability, okay, before it is used, it might go this way. This is my original configuration, so this is a final configuration under this load. So another one is stability, maybe local, global, elastic, and plastic bending or torsion. So you can see this one is another instability, and you can see if you apply the compressive load, and you can see how this is a U-shaped. We can call the two is a structure that deforms. The shock and impact. Shock and impact are the collision of two masses with initial relative velocity. The shock, ascendant applied force of disturbance. So we just talk this one. So here is the shock and impact. Okay, so this is the This is simplified version. We have a mass here. This is our reference point. And so this is a spring, and this is another spring. So this is the mass 1 and mass 2. So x1 is the displacement of m1, x2 is the displacement of m2. So this is equations. So because we have these are two mass, right? So this is we can have these two equilibrium equations. Now, because there is the shock, the velocity, the acceleration is there. Acceleration is not negligible anymore. So you need to have this acceleration. This double dot means the second derivative of the displacement, which is acceleration. So first dot is the damping. So first dot is the velocity x1 or 2. First dot is the velocity. Velocity multiplied by damping coefficient. That is also needs to be considered. But here we just ignore the damping effect. Any question regarding this one? I will not test your understanding, but so this is just to expand your knowledge base. Right? So you know that we have some equations here. So the standardly applied load. If we have a beam here, so there's a weight, and we just release the weight, and we know that this weight will be accelerating because of the gravity, and then at this point it will hit this one. So this is a shock. This is a standardly applied load. So this is very, very complicated. Okay, so standardly applied shock, and we have so these equations. This is the actual problem. So here we can just treat this beam as a spring to simplify this problem. So here is all these equations are here. You can calculate. This is solving the delta. So this is a deflection. Maximum deflection is also given. How much you can have W over K. K is